Coming to module 2, that is water and buffers. So in this module, the topics given in the syllabus, that is the properties of water and the solubility and ionization of water, pH and the buffers and their importance. So the first part we discuss about the properties of water and the ionization. The second part we discuss about the what are acids and bases according to Arrhenius, Bronsted-Lowry and Lewis theory. What are strong acids and strong bases? Then why we use only the weak acids and weak bases for the making the buffer solutions? Why not strong acids and the strong bases? And we also discuss about the Henderson-Hasselbalch equation and its importance for the preparing the buffer solutions. Now, coming to this, as we know that water is the predominant chemical component of all living organisms, and most of the cells are surrounded by water. If you take in the cell itself, it has 70 to 95% of the water, and that is the main reason why the abundance of water is the main reason why the earth is habitable. And coming to the medical and biological importance of the water, and as it is the essential constituent of all forms of life, means it is present in every cell, and it is the medium in which all the cellular reactions or the biochemical reactions takes place. It is required for the many biological process such as mechanism of enzyme action, the transport of molecules in the body. So water is a medium. And in addition to this, we have already discussed when I explained about the protein three-dimensional folding. So as we have already said that the protein structure, primary, secondary, tertiary, and the quaternary structure. And the tertiary structure is the three-dimensional folding of the protein. So when the protein folds in the cytoplasm, so if this is the cell, and when the protein folds into in the cytoplasm, that is in the aqueous environment, and as I already clearly mentioned that when the protein folds in the cytoplasm, you can see here that the hydrophobic amino acids are buried inside, whereas the only polar amino acids or the hydropolar amino acids stay on the surface, because the cellular environment is aqueous. So that means once the protein is folded, and this folded protein is surrounded by a layer of water molecules. I think this I had already made it very clear when I explained about the three-dimensional structure. So that means here the water facilitates the folding of the polypeptide chain into its three-dimensional structure, because the hydrophobic amino acid doesn't like in interacting with the polar water molecule. Therefore, they are buried inside, and whereas the polar amino acids stay on the surface and interact with the water that is surrounded by the surrounded. So this water layer is also known as the hydration shell or the water layer. So that means the water helps in the folding of the biological molecules, mainly like proteins and nucleic acids and so on. Then, and of course, the semi-fluid nature of the body is due to water, and it regulates the body temperature, and it accelerates the many biochemical reactions by providing ions. And the water content in the body alters in dehydration and in edema. And so that means it has many functions in the body, and many reactions takes place, and so on. But the water has unique physical properties, in the sense these unique physical properties include it has the ability to solvate a wide range of organic molecules. That means many molecules many molecules or many compounds dissolves in water, because it has the ability to solvate many organic and inorganic molecules. And it has the exceptional capacity in forming hydrogen bond. So we know that water can form hydrogen bond with another water molecule. In addition to this, it can also form hydrogen bonding with other molecules. So that means it has the exceptional capacity for forming hydrogen bonds. And it is also an excellent nucleophile. And in many metabolic reactions, the water acts as serve as the reactant or the product. And in the human body, the water or the content or the regulation of water is done by the hormone, anti-diuretic hormone. So that means the water the balance is mainly done by the anti-diuretic hormone. And then coming to this, in addition to this, the water has the propensity to dissociate into hydroxide ion and also the proton that we know, and water dissociates into H plus and OH minus ions, and the concentration of the proton or the acidity of solution is generally reported by the logarithmic pH scale. This we will see later. And since most of the reactions in the cell, most of the reactions that takes place in the cell takes place in the water medium, that is aqueous medium. So that's why the physical properties of water influence the many biological systems. So to understand this, we need to understand the properties of water thoroughly. And we know that water is a polar molecule. So that's why, as I already said, that since it is a polar molecule and it has the ability to solvate or it has the tendency to wet substances. So in the sense, since it is a polar molecule, it has the tendency to solvate many compounds or it has the tendency to wet substances. So what makes the water polar? So we know that when we say that polar or non-polar, and in any molecule, if the bonding electrons are shared between the two atoms equally, then we say that it is not polar. So if the bonding electrons are not equally shared, then the electrons are pulled towards the one atom which is having the higher electronegativity. So in such case, we say that there is a polarity. So in case of water, the water has the central oxygen atom and two hydrogens. And if you see the electronegativity of this hydrogen and oxygen, the electronegativity of the oxygen is 3.5, whereas the electronegativity of the hydrogen is only 2.1. So because of the difference in the electronegativity, and oxygen gets minus delta charge, whereas the hydrogens get delta positive charge. So that means because of the difference in the electronegativity, these electrons are attracted towards the higher electronegative atom, that is pulled towards the oxygen, as therefore oxygen gets a minus delta charge, and whereas the hydrogen gets delta positive. As a result, the dipole moment is created. Therefore, this dipole moment or the dipole is responsible for its polar nature of the water molecule, because the positive end of this dipole in the water interacts with the negative end of the another molecule having the dipole. In the same way, the negative dipole of the water can also interact with the positive end. So that's why the water molecule is polar. And now coming to so when the electrons are unequally distributed, as we know that these partial charges gives results in the intramolecular force that is known as the dipole force. So that in the dipole force, as I already said, that the positive end, so the positive end and the positive end of the one molecule attracts the negative end of the another molecule, and the intermolecular force is known as the hydrogen bonding. This we will make it a little more clear in the later. And so now we know that in case of methane, you can see here in case of methane, it has the 4 carbon hydrogen bonds, and the electronegativity of the carbon is 2.5, and the electronegativity of the hydrogen is 2.4. That means it is the electronegativity of the carbon and hydrogen almost nearly equal. So that's why the here we don't see any dipole here. So that's why this methane is a non-polar molecule. And in case of carbon dioxide, you can see here in case of carbon dioxide, though carbon dioxide has the carbon has the electronegativity of the carbon is 2.5, the electronegativity of the oxygen is 3.5, but because since it is a linear molecule and the dipole becomes 0, so as a result it has it shows the non-polar nature. And as you can see here that if in any molecule, if the two atoms have the electronegativity difference between 0.4 to 1.7, then we consider that as a polar covalent bond. But only here the only difference is that water is a polar, but the carbon dioxide is a non-polar, because the carbon in case of carbon dioxide, the molecule is in a linear, and therefore the dipole in a carbon dioxide molecule linear, so that means it cancels each other. So as a result, that gives the non-polar nature to the carbon dioxide molecule. And now coming to the solvent properties of water, and we know that some compounds or the substances dissolve in water, some substances doesn't dissolve in water. So why do some compounds dissolve in water while others not? So the reason is that, as I already said, that most of the ionic compounds, like you can see here, most of the ionic compounds like KCl and low molecular weight polar compounds, polar covalent compounds like ethanol or acetone, and they dissolve in water, because all these molecules have a dipole, and these dipoles, either positive or the positive end or the negative end of these dipoles, interact with the positive or the negative end of the dipole of the water molecule. As a result, the water these molecules are dissolved in water. These compounds dissolve in water. So in the same way, so in this during the reason behind the this solubility, or the solubility, is that either either ion dipole interaction. For example, in case of inorganic molecules, so the KCl has a K plus and Cl minus ion, and the K plus, this is the positive dipole that interacts with the negative dipole of the water. So therefore, in case of KCl, it dissolves in water because there is a ion dipole interaction. This is the ion and this is the dipole. So ion dipole interaction is present. So in case of other polar organic molecules like ethanol or acetone, they also dissolve in water because there is a dipole interaction is present when these between the ethanol or water, and ethanol or acetone and water. And so that's why they dissolve in water. That means in inorganic compounds like KCl, the ion dipole interaction is present, takes place, whereas in case of organic the polar compounds, the dipole interaction takes place. You can also see here when the any ionic compound, when it is dissolved in water, and they dissolve in water, and as a result you can see here the negative the dipole of the ion interacts with the positive dipole of the water, that is H plus. In the same way, it and the positive dipole interacts with the negative dipole of the water. So that's why these ionic compounds dissolve in water. And as I already said, that you can see here the in case of KCl, so dipole interaction, you can clearly see here this is the KCl. When in water it dissociates in the K plus and the Cl minus, and the K plus this ion interacts with the negative dipole of the water. So that means the negative end of the water dipole attracts the positive ions, and in the same way the negative end, the negative ion is attracted by the positive end of the dipole. So in the same way, you can see in case of polar compounds like alcohol or ketone, you can also see here same thing. You can notice that they have the dipole type of interaction here. Because these polar molecules also have the dipole, so they have the dipole type of interaction, whereas in this case ion dipole interaction. So that means this ion dipole or the dipole interactions are responsible for the polar or the ionic compounds to dissolve in water. And since many some molecules or some compounds dissolve in water, some compounds do not, or the compounds which dissolve in water, they are also known as the polar compounds are the hydrophilic. So because they have the tendency to dissolve in water because of the either ionic or the dipole interactions. And whereas in case of some compounds that doesn't dissolve in water, they are also known as the non-polar or the hydrophobic molecules. And because the ionic and the dipole interactions are not occur in case of non-polar compounds, that's why they are also known as the hydrophobic molecules. And some compounds are amphipathic in nature, in the sense these compounds have both hydrophobic as well as the hydrophilic regions. For example, you can see here, this is the palmitic acid. As we have already discussed in the yesterday's class, the palmitic acid is a fatty acid. It is sodium palmitate, and you can see here this has the hydrophobic tail, and it has the hydrophilic head group, and the polar head group as well as the non-polar tail. So when such molecules are dissolved in water, they form cells. As I already yesterday I told, micelles are these single layered spherical structures, single layered spherical structures. In this, the head groups are exposed to the aqueous environment, whereas the hydrophobic tails are buried inside. So that means these amphipathic molecules in water forms the micelles. That you can clearly see here, that as I already said, that the hydrophobic residues, the hydrophobic tails doesn't favor in interacting with the water. Therefore, they escape in interacting with water in such a way that they are pushed into the inside, whereas the hydrophilic head groups are present on the exposed to the outside. Therefore, the hydrophilic head groups are outside and the hydrophobic tails are inside. As a result, these the amphipathic molecules form micelles. And so then coming to there are some examples for the hydrophobic and hydrophilic substance. As I already said, that hydrophobic means non-polar. They are not dissolved in water because no ion or the dipole type of interactions takes place between water and the molecules. Whereas in hydrophilic, so they are also known as the polar molecules. They dissolve in water because the reason for their solubility is the either ion or the ion dipole type of interactions. And the hydrophilic compounds, you can see here the polar covalent compounds like alcohols or the ketones and the acetone. All these are polar compounds, they dissolve in water. In the same way, sugars, ionic compounds like KCl, amino acids, phosphate esters, all these molecules are hydrophilic compounds, are hydrophilic in nature because they dissolve in water, and they form either, as I already said, that either ion dipole or the dipole type of interaction takes place. So that's why they dissolve in water. And coming to the non-polar covalent compounds, like hydrocarbons, like hexane, or the fatty acids and cholesterol, these compounds are hydrophobic in nature, so they are not they don't dissolve in water. And so in summary, the water is a polar molecule because of the irregular distribution of charge, that is the partial negative charge on the oxygen and the partial negative charge on the partial positive charge on the hydrogen. And these negative charge of these partial positive charge and the partial negative charge of the water molecule can interact with the other molecules by dipole or the ion dipole interactions. And the polar molecules or the hydrophilic molecules dissolve in water, whereas the non-polar molecules do not. And whereas the properties of water have the direct effect on the behavior of the biomolecules, as I already said that the water aids in folding of the biological molecules, as I said, the forming the three-dimensional structure of the protein. And so this is about this one. Then coming to the water molecules, have the, as I already said that at the beginning itself, the water molecule has the exceptional capacity for forming hydrogen bonds. So this water molecule, you can see here that we know what is the hydrogen bond. That is a interaction between the dipoles. And here, the positive end of one dipole, if the positive end of the one dipole interacts with the negative end of the another dipole, and in this you can see here that, so the water molecule, in a water molecule, this is these lone pair electrons present here, they serve as a hydrogen bond acceptors. So in the sense, these serve as a hydrogen bond acceptor, and this hydrogen serve as a hydrogen bond donor. That means water molecule can serve as a two hydrogen bond donors and two hydrogen bond acceptors. So that means each water molecule is involved in forming the four hydrogen bonds here. So this is the first one hydrogen bond, and this is the two hydrogen bonds, and 3 and 4 here. In this case, this water molecule is serving as two hydrogen bond donors and two hydrogen bond acceptors. So that's it. That therefore, each water molecule is involved in forming the four hydrogen bonds, two as donors and the two as acceptor. And because of this arrangement, the tetrahedral, due to this, the water molecule gets the tetrahedral arrangement. And in the so when the in the liquid water, these hydrogen bonds you can also clearly see here, these are the two hydrogen bond acceptors here, and these are the two hydrogen bond donors. And these hydrogen bonding also varies from the molecule. You can see here the hydrogen fluoride. It has this is HF, and this hydrogen fluoride has one hydrogen and the one fluorine, and it has the three lone pair electrons. And you can see here, and this hydrogen fluoride can serve as one hydrogen bond donor, and three hydrogen bond acceptors. So in the same way, if you take water molecule, as I already said that the water molecule has two hydrogen bond donors, and you can see here, this is the one hydrogen bond donor and this is another hydrogen bond donor, two hydrogen bond acceptors. So in case of ammonia, it has three hydrogen bond donors and one hydrogen bond acceptor. In the sense, so these so that means this also dictates its various properties. And in case of the liquid water, these hydrogen bonds constantly form and constantly break, and so that means it can, the cluster can break and reform 10 to the power of minus 10 to 10 to the power of minus 11 seconds in water at 25 degrees centigrade. That means these hydrogen bonds continuously form and continuously break, and these hydrogen bonds are much weaker compared to the covalent bonds. We know that covalent bonds, the formation of the covalent bonds and the disruption of the covalent bond require higher energy. You can clearly see here, and the covalent bonds, and whereas the non-covalent bonds like hydrogen ion dipole, hydrophobic, as well as van der Waals forces, they are the weak forces compared to the covalent bond. And in case of hydrogen bond, the bond energy is the 20 kilojoules per mole or 5 kilocalories per mole, and which is lesser than the covalent bond energy of the covalent bond. And this hydrogen bonding, since the water is it has the exceptional capacity in forming hydrogen bonds with other water molecule and also the other. So if you see the melting point and the boiling point of water is, you can see here the boiling point is very high compared to the other molecules of similar close molecular weight, such as ammonia and the methane, because the water has the exceptional capacity forming the hydrogen bonds, and that's why, and it has the higher boiling point. And so compared to the ammonia and the methane, the interaction between the water molecules is stronger and with hydrogen bonds. That's why it has the higher boiling point. And these hydrogen bonding not only present between the water molecules, the hydrogen bonding is also important in stabilizing the structure of the many biological molecules like DNA, RNA, and proteins. As I already said, that in many biological molecules, these hydrogen bonds are involved in the stabilization of the three-dimensional structure of the biological molecules. And like the protein and the DNA are, you can see here, in all the protein is stabilized by the hydrogen bonds present between between the polar and the acidic amino acids, and they are present in the proteins. In the same way, the DNA is these bases are linked to one another by the hydrogen bonds in the same way. So that means the hydrogen bond. In summary, the hydrogen bond is a type of dipole bond, and water molecules are extensively hydrogen bonded, and they can form hydrogen bond with other water molecules. These water molecules also have the ability to make the hydrogen bond with other molecules. So that's why it has the unique characteristics. And this is also the reason why it has a very high the melting point and also the boiling point compared to the other molecules of close molecular size. And the three-dimensional structure of the many important biomolecules like protein, nucleic acids are stabilized by the hydrogen bond. So that is the importance of the hydrogen bonding. Now coming to I think before going to the acids and bases, let us discuss about the ionization of water. As we know, this water, when it dissociates in ionization of water, since water is a amphoteric substance, that means it gives both H plus and OH minus ions. So that means water molecule, when it dissociates, it gives H plus and OH minus. So the ionization of water can be described by a dissociation constant, that is the Kd, and the dissociation constant Kd is equal to concentration of H plus and concentration of OH minus divided by concentration of water. So this is the simplest way to represent the dissociation of water, and this same dissociation, see this the same thing we can also represent in another way, that is since where proton is highly reactive, again it reacts with another water molecule and forms the hydronium ion. So therefore the another way to represent this is that when the bare proton interacts with another water molecule, it forms the hydronium ion and OH minus. Therefore, we can also represent the ionization of water with this. And now, in ionization of water, when we say that it gives the both H plus and OH minus ion, and the dissociation constant Kd depends upon the concentration of the H plus and the concentration of OH divided by the concentration of water. But in pure water, the H plus ion concentration is 10 to the power of -7 molar. In the same way, the OH minus ion concentration is also 10 to the power of -7 molar. 10 to the power of -7 molar. So therefore, from this, the molarity of the water can be calculated. The molarity is equal to number of moles of water divided by the volume, that is 1 liter. So therefore, the number of moles, we know number of moles is equal to weight by the molecular weight, and here the weight of the 1 liter of water, is 1000 grams divided by 1000 grams, and divided by the molecular weight is 18. And if you substitute here, and we get here the 55.6, so that is the molarity of the water. So coming to the ionic product of water, so in ionic the ionic product of water, Kw, the ionic product of water, Kw W is equal to concentration of H plus, concentration of OH minus. We know, as I already said, that the concentration of in pure water, the concentration of H plus is 1 into 10 to the power of -7 molar, and the hydro OH minus and concentration is again 1 into 10 to the power of -7 molar. Therefore, the Kw is equal to 1.0 into 10 to the power of -14. This is the Kw. And from this, we can also calculate pKw, that is minus log Kw, that is equal to minus log 1 into 10 to the power of -14, that is equal to 14. So that means Kw is 1.0 into 10 to the -14, and pKw is 14. So this is the ionic product of water. So now, with this background, now we discuss about the buffers and the pH. We need to understand a little bit about the acids and bases. So now, though it is not important to discuss the details of all the theories, but we know that the properties of bases explained by 3 theories. One is Arrhenius theory. According to Arrhenius theory, we know that substances which can produce H plus ions in solution, they are acids. For example, like HCl and H2SO4. In the same way, substances that can produce OH minus ions in solution, they are bases like NaOH and BaOH and so on. So that is according to Arrhenius theory. According to Bronsted-Lowry theory, we know according to Bronsted-Lowry theory, the proton donor is proton donor is acid, whereas proton acceptor is base. So that is the according to Bronsted-Lowry theory, proton donor is acid, whereas the proton acceptor is base. So according to Lewis theory, the electron pair acceptor is acid, whereas electron pair donor is base. So these are the this is the overview of the acid-base theories according to Arrhenius theory. So the substance which can produce hydrogen ions in solution is acid, whereas the substance which can produce hydroxide ions in solution are the bases. And according to Bronsted-Lowry theory, the proton donor is acid, whereas the proton acceptor is base. And whereas according to Lewis theory, electron pair acceptor is acid and electron pair donor is base. And of course, we can give many examples for the Lewis acids like the NH4 plus or the even H3O plus hydronium ion or the Mg2 plus. All these are the Lewis acids. And in the Lewis bases, again we have the NH3 and the OH minus, F minus, and so on. All these are the Lewis bases. And now coming to the weak acids and weak versus strong. Weak versus strong. So we need to understand what does mean by weak and what does mean by strong. So we know that strong acids, for example, we know that strong acids and strong acids dissociate completely in water. Strong acids or strong bases dissociate completely in water, whereas weak acids or weak bases dissociate partially in water. So that means strong acids, for example, HA, if it dissociates H plus A minus, so that means it dissociates completely in water. That means it has for a strong acids, the equilibrium is towards right. The equilibrium is towards right. For weak acids, for example, acetic acid, you take acetic acid, weak acid, acetic acid, it dissociates into CH3CO minus plus H plus. For weak acids, the equilibrium is towards left. So that means strong acids dissociate completely in water, whereas weak acids dissociate partially in water. So from this, the strength of acids can be represented with acidity constant or the acid dissociation constant. For example, if it is in case of HA, if it is acid, when it dissociates, it forms H plus and A minus. The acidity constant Ka is equal to concentration of H plus, concentration of A minus divided by concentration of HA. Concentration of HA. So from this, you can understand that, as I already said, that for strong acids, and let us we consider only here the weak acid. For strong acids, the equilibrium is towards right, and for weak acids, it is towards left. So that means when the equilibrium is towards right, and in this case, the products are more compared to this. So that means the strong acids dissociate completely in water. Therefore, strong acids have higher Ka values, whereas weak acids have lower Ka values. So that means so if the acid has higher Ka, that means it is strong, And if the acid has a lower Ka, so that means it is weak. So that means because higher Ka means they dissociate more, whereas the lower Ka means dissociate partially. But the strength of the acids and bases in general is expressed with a different expressed instead of K values, it is expressed with pKa. So one more point for strong acids. For strong acids, the Ka value is in the range of up to 10 to the power of 10 to the power of. For strong acid, the Ka value is 10 to the power of. For strong acids, for strong acids, the Ka value is approximately up to 10 to the power of 15. For weak acids, the Ka value is 10 to the power of minus 60. That means higher Ka means strong, lower Ka means weak. But the acid strengths are generally expressed using pKa values. Instead of Ka, the acid strengths are expressed using pKa values. That means we know pKa is equal to minus log Ka, like we know pH is equal to minus log H plus. So from this you can see here strong acid and weak acid. From this we can understand that strong acids have higher Ka and lower pKa. Weak acids have lower Ka and higher pKa. So because when the Ka is higher, obviously it's a logarithmic pKa is lower. So that means if the acid is strong, means it has higher Ka and a lower pKa. If the acid is weak, it has a lower Ka and a higher pKa. So from that means by Ka and pKa values, we can understand that whether a acid is a strong or a base. As I already said that the strengths are normally expressed using the pKa values rather than the Ka values. So this is about the overview of the three theories of acids and bases and the what exactly meant by the strong acid and weak acid, or strong base or the weak base. So the strengths are expressed using the dissociation constant Ka or the pKa, but the normal way of expressing the acid strength is using the pKa values.